is going to be a bit more technical than the others because we can't keep talking about things in general terms. We have to get down to some specifics to justify the claims that we've made. So this talk will be a bit more technical than some of the others. And then we'll have a well-earned lunch after that. So this is called Beyond Turing, the Universal Rewrite System. Now the aim of our cybernetics machines group is to tackle fundamental questions which we think are related. And a lot of these questions have been around for a long time without a great deal of progress. So is it possible we can use new methods to get an insight into these questions and get some sort of answer? I have to tell you that I'm a physicist, a theoretical physicist, that I got into this through trying to explain physics. I also got into biology through trying to explain physics, and I've also got into mathematics through trying to explain physics. So all these subjects appear to be connected. Now, there's no question that computer logic and the Turing machine has been a fantastic success story. You don't need very much command structure to accomplish incredible tasks, like beating grandmasters at chess and so forth. But it's not obvious that the world is structured according to the Turing machine. And it's not obvious that the human brain is. There's no obvious transition from the logic of the digital machine to the self-organization that you get in a natural system. And typically in biology, physics, chemistry, and different areas of that kind of work. So it's not obvious that there's that connection. And so could we simply, by increasing the processing power of the digital logic machine, create a state of consciousness? Will it emerge through simply increasing the processing power? Well, I don't think it will, and many other people don't. But nevertheless, the universe seems to be based on information systems. What we're doing with our Turing machines is in fact some sort of copy of what the world is like. But it's not an exact copy, there's a difference. There's some kind of program, and it's similar to that of a digital logical machine, but it seems also to be in some way different. So perhaps there's some kind of missing ingredient which we need to make the transition. Now, the automatic response of the human mind when it comes to a problem like this is to think of something complex. We're often inclined to think that way, something more complicated than we've got, but nature doesn't seem to do that. It goes for simplicity. And the answer may not be complicated at all. It may be something that we've missed that's profoundly simple. So, clearly, we should ask these questions. But we believe in our cybernetics machine group that we can get the answers to these questions, or at least find a route towards them. The humans have developed a very powerful information processing system with our digital logic, but is this nature's own information processing system? And if it isn't, what is the difference between them? Now, it so happens that I've been looking at these information processing systems simply because I've been looking at my own subject areas of interest, mathematics, physics, and biology, and to a certain extent chemistry. And I have been trying to work out their intrinsic logical structure. And these researches and those of my colleagues suggest that there is an information system. It's a particular one, a very special one. And all the knowledge of the world, all the processes that happen in nature follow this information processing system. It repeats itself at every level. So the same information processing system works in physics and in biology and in the human brain in some way. We think that it operates the same way and that it can be described exactly and with technical precision. We feel that we can show that it makes sense of great areas of these subjects. and also ensure that we get a self-consistent mathematics, overcoming things like the Gödel problem. And incorporating the digital logic of our computer systems as a special case with specific restrictions. So we're looking for something more general, which includes what we now use as computer logic. There's no point in contradicting that, that's obviously true. But we want something more general which incorporates it. And we want to see how self-organization and emergence happen naturally. We think we can do this. We also think that we can suggest some of the ways in which a biological organism, like the brain, differs from a classical Turing machine. So that helps us to understand both. And we think the proof will be seen in the way we can create foundations for mathematics and the natural sciences, show how they're connected, and then get many specific results. So we're making big claims here, but we think we can justify them. So we will describe the process in technical detail. It's no use talking about a process unless you describe what it is. And we're going to describe it exactly as it happened. This will be a little bit technical, but not too technical, we hope. But what is the simple idea? I said earlier that I thought there may be a simple idea. What is that simple idea that underpins it? What's this key ingredient? Why is this information processing system different from and more comprehensive than the standard digital logic? Well, it's very simple to say what it is. And then we can explain why it is like this. Digital logic uses the symbols 0 and 1, and the active element is the 1. And the 0 is the passive element. So everything is based on 1s against a background of passive zeros. Now we believe that nature's logic, if we may call it that, is based on an active 0, from which all of the symbols, including 1, are derived. And this will account ultimately for the differences that we observe between natural and artificial systems. And we think the 0, the active 0, introduces the semantic element, which is missing from the more syntactic processing of formal logic, the thing that has what we call physical meaning. So the logic is based more on 0 and 0 rather than 0 and 1. And there's a fundamental philosophical principle behind this. You have to start from some principle. And the principle this starts from is a universal constraint of totality 0. Every system always works towards totality 0. The universe works towards the totality 0. And this is done in a systematic way. And this creates a process which appears to be similar in the way that many natural processes appear to operate. And we develop a kind of natural logical grammar. This generates digital logic, but isn't confined to it. So it's more comprehensive, but it doesn't contradict digital logic, far from it. So let's go to the way we normally talk about computation, in the usual way we talk about it. Uses a language requiring a grammar. This is discussed by Chomsky in the 1950s. And this language or grammar has an alphabet or vocabulary with symbols. And it needs a start symbol, terminal elements, and production rules. And the syntax of the language, which is about the production rules, can be considered separately from the semantics. The programmer supplies the meaning, the semantics, but the syntax is done by the computer. Now, the Turing thesis says that computations based on such grammars can always be carried out on a Turing machine. And any computation using digital logic can always be related to computation on a Turing machine, without exception. And we can even construct a universal Turing machine to simulate the computations of every other Turing machine. And a Turing machine gives us a finite set of states, an alphabet with a blank symbol, a starting state, and a set of transition rules. Now, if we can consider all computation to be equatable to computation using a Turing machine, we can use this as the basic requirements for a computation or computational grammar on such a machine. And theorists have put forward the elements that we need for such a grammar. And it's called a rewrite or production system, and this is standard computing theory. This is the basis of all programming and algorithmic processes of any kind. Essentially, a conventional rewrite or production system has 4 fixed components. An alphabet, that's all the things that we can deal with. A rewrite rules or productions, some starting axiom or symbol, and stopping criteria. Sounds relatively simple to express it in that way. Now, all such systems and the Turing machine itself are known to encounter what we call the halting problem. So we can't tell whether from a given input the program will eventually stop or enter into an infinite loop. I'm sure we've all had that problem of it entering into an infinite loop more than once. So let's give you an example. This is a standard, this is nothing to do with our theorizing, this is standard rewrite procedure. We could devise a process for generating Fibonacci numbers, for example. Let's have 2 rules where we have an alphabet with A and B, and we have 2 rules, A goes to B and B goes to AB. The first generation we start with a single symbol A. So that's a start, we've got our production rules, we've got our alphabet. The first rule then tells us A goes to B, and then the second rule tells us B goes to AB, and we carry on BAB and so forth. And you can see the length of the string becomes equivalent to the Fibonacci number. And that's a standard process, and we just decide to stop it arbitrarily at whichever point we want to stop it. And that would be our stopping criterion in this case. Now, what we have done is find that what we think we might call nature's programming system is very similar to this in many significant ways. But it also exhibits distinctive differences. We can imagine a system in which all 4 elements, alphabet, start object, rules and criteria, and stopping criteria, can be varied. So this is still a rewrite structure, still got an alphabet, still got a grammar, but now it's universal. And it's also self-generating. And this is the difference between this and the alphabet, grammar, etc. we use for Turing machine. And the basis of this is the assumption, which I stated before, this is based on a lot of philosophical reasoning, that the universe, or any alphabet which it contains, is always a zero totality state. There's no unique description, and it's infinitely degenerate. So we've got a zero totality state at all times, in every case. But it's not fixed. There's no particular one that expresses the whole system. It's always zero totality, but that state is infinitely degenerate. And we have to continue to regenerate the alphabet in such a way that it is always new. And without any limit or stopping criteria, you just arbitrarily stop where you want to stop. As the new state created is always another non-unique zero totality, so you never stop. I'd like to think of it as a kind of zero attractor. That's a very popular word, attractor, in computing, so let's call it a zero attractor. Now, if we've got a non-zero deviation from our starting 0, whatever that may be, let's call it R, for example, that will always incorporate an automatic mechanism for recovering the 0. So let's call it the conjugate, or star, whatever that may mean. And the zero totality now results, but it's not unique, and it necessarily requires a new structure. Now, by the way, this system came out of physics This was intended to explain a physics that already existed, a fundamental theory of physics based on algebras that already existed, and I worked with a computer scientist to recover this structure, and in the process of trying to apply a rewrite structure to this physics and algebra, it turned out that we had something bigger than we intended. Also, we think anyway. So then it took a time to codify this and work out how it actually operated. But we ensure a structural alphabet is new by defining the position of all previous structures. So how do we know our alphabet's new? Well, the previous structure must be incorporated within it. So we start with something and we build a bigger box and build a bigger box and so forth. And we always incorporate the previous one in it as a kind of sub-alphabet. And so we know that it must be new because the new alphabet contains new things apart from the original. If we just change the symbols, it could have been the old alphabet under new symbols. But if we incorporate the old one, we know that it must be new. So what we're doing is defining a series of cardinalities. You will have heard of the Cantor argument about cardinalities of infinities, infinity containing a bigger infinity and so forth. This is similar, but it's cardinalities of zeros. So successive alphabets absorb all the previous ones, so there's a new cardinality. And if you like, all transitions from one alphabet to another can be seen as a kind of bifurcation, a kind of doubling. And that will be important in the physics later, and in the biology. Now, there's lots of ways of representing this sort of process, but just one possible one is to concatenate or place together with no algebraic significance of any given alphabet with respect to any other with its components or sub-alphabets. So if we define an alphabet to a cardinality as a cardinality, what cardinality means everything. So anything other than itself must be a sub-alphabet. And if we concatenate the sub-alphabet with the alphabet, so we take the elements of the alphabet, whatever they may be, put them against the alphabet, concatenate them, we should produce nothing new. This concatenation process doesn't have to be concatenation, we just choose that for simplicity. However, since the alphabet has to renew itself, we decide that concatenating the entire alphabet with itself produces a new cardinality, or zero totality alphabet. So let me show you how it does. Let's use a couple of symbols. You don't have to use symbols. This is just one method of doing it. It's just a representation of something we think is more fundamental than you can actually represent. So I'm going to use that double arrow for two aspects of the process. It's not two processes, it's one process. But there are two aspects. Let's use the double arrow for create. Every alphabet produces a new one, which incorporates itself as a component. So we've got alphabet and itself concatenate new alphabet, incorporating itself. And then a single arrow for the conserve, which means that nothing new is created by concatenating with the sub-alphabet. This is a little technical, but I think it's so important to do this technical thing at the beginning, so we know that we're talking about something that we can express in a technical way. So if we look at the first line there, sub-alphabet concatenated with alphabet gives us alphabet, nothing new. And that's because an alphabet is a cardinality. So from within itself you can't find anything new. However, since that alphabet isn't the end of the story, we concatenate it with itself and we get new alphabet. Zero totality is not unique. So that's the basic processes which we're going to talk about. So I'm going to start with a zero totality alphabet. This isn't necessarily the beginning, it's not the beginning of anything, it's just the beginning of where we start. Because nature does this all the time. Every end is a beginning. There's no such thing as the beginning. It just carries on from wherever we start. So this is an already bifurcated state because we've got R and R star in it, because it's a totality zero. And we will presume it started from a previous alphabet, but let's assume we don't know anything about that previous one. We've no structure for it. Doesn't mean there isn't one, we just don't know anything about it. So if we describe whatever it was as R, then the R star character creates the doubling process. Now, we talk about doubling, bifurcation, in terms of the number 2, because we're taught to do numbers from our childhood, 1, 2, 3, 4, 1 and 1 is 2 and so forth. And we got it so ingrained in us that we can't imagine something before numbers. But you have to imagine that there aren't any numbers. There isn't any 2. There are no numbers yet. There's just alphabet. So even though we might use the word bifurcation or doubling or duality, then we can't assume that we've got any numbers. There's no assumption here that there are numbers. It's just that we haven't got words to express it without using what we've been conditioned into. So we assume R is a zero totality alphabet, but a zero of which we have no access. So it's difficult because we're trying to posit that there's an ontology before we even begin our observation process. So we assume it happens without us being able to observe it. Now let's apply the conserve process to concatenate R star with its sub-alphabets, produce nothing new. Now clearly we've got to distinguish R and R star, but we've got to produce nothing new. And so if we apply that structure, then we can make it work. Effectively, we produce nothing new, but we produce a new order there, such as that means anything. Okay, and we can then produce rules by which this will work. Okay, so that's how we start. So the next stage is to show that this alphabet isn't unique and that it concatenates with itself and produces a new zero totality alphabet. And we've got to guess what it might be. We can't assume that it's something like A star because we've got to include the previous alphabet to show that it's not new. That it's new, sorry. If I just put A star, that's new. That's not new, that's just redefining symbols. The only way we can ensure it's distinguishable from the old one is by incorporating the old one. And so we do this, so we try this. Does that work? Can we break? Now, what we always do is when we do a create process, we have to do the conserve process at the same time to see if it works. So let's do that. So this is the conserve process. We try all the sub-alphabets. Does it work? Are all these terms different? All those terms different? Because if they're not different, it's nothing new. But do they produce the same result? Yes, they do. So we can make them all different, but produce the same result. Oh, we can get away with that. That will work. Okay? But it can only be different if AA becomes R star, while RR becomes R. So you see, we've already distinguished R and A. They have to behave differently, otherwise we created nothing new. I don't think I need to go into too much detail about that. I'll leave that slide and go on to the next one. Now we've got the next stage. Can we do it again? Let's try this. It fails. Because the conserve mechanism forces us to introduce new concatenated terms like AB and AB star. And these are outside the alphabet. So the only possibility is to include these in advance and to do something like this. Okay, sorry. Does that work by the conserve process? So it works if we try the first 6 terms, there's no problem. We get everything is different, and we get the same total result. So that's okay. But we've got a problem when we get to this. If we can use the concatenated terms on themselves and on each other, we're left with 2 options. We can call these commutative and anti-commutative. And this is the commutative one, this is the anti-commutative one. We think, which do we choose? Well, in fact, there isn't any choice, because if we choose the commutative one, we don't get anything new. Only the anti-commutative one produces something new. I can leave you to that as an exercise for the reader afterwards to work out why. Now, labelling is arbitrary in this rewrite, so it doesn't matter what labels you use. Labels A and B can't distinguish things. They can only be distinguished by outcomes. And if the outcomes aren't different, then they can't be distinguished. In this case, the outcomes aren't different. In this case, they are. So it's the only way we can do it. And then if we do that, yes, we can make that make sense. A and B are indistinguishable except by labelling. They don't extend the alphabet. So we default on the anti-commutative option, which means the last two concatenations become those. And now this one does work. However, we can't do it again. We can't do it again for C and D, because we'll always get an inconsistency. We can't build C and D into this structure. What we can do, though, is see what happens. Anti-commutativity produces what we call a closed cycle. We get components AB, and the conjugates, and you can't get any other terms in on that. It's a well-known, if you do it mathematically, it's a well-known mathematical problem. However, what we can do is have successive cycles of these. We do it for A and B, and then we can do it separately for C and D. And these can be commutative with each other, but anti-commutative within themselves. And we can do that indefinitely. And suddenly, we now have an infinite alphabet. We can do it indefinitely. We show that C and D are unique because each has a unique partner. So they prove themselves unique by having unique partners. The successive alphabets can be seen as a regular series of identically structured closed anti-commutative cycles, each of which commutes with all the others. And so we've got an infinite alphabet of zeros. And we can say that's the same structure as we get with binary integers of conventional mathematics. Each alphabet represents a new integer, new 1. 1, 1, 1, 1, 1. So we can say this generates binary numbers. The binary symbol 1 is generated by this process. You can call it 1 if you like, it doesn't make any difference. They're all unique. All the ones are unique. And also, it's also the classical Boolean logic state as well. So mathematics and digital logic become emergent properties of this. There's no defined starting point, and we can reconstruct it endlessly in a fractal manner with self-similarity. And it's the zero attractor which makes it possible. Now, we can do many representations of this series, and we will do, because we do need it for different purposes. But a very convenient one is the mathematical one. If we can create a discrete integer system by this process, then we can also generate an entire arithmetic and algebra. The rest of the constructible numbers follow automatically. Yeah, and I'm just explaining how you get real numbers in the Cantorian sense. So let's explain this as an iterative process. So this is an iterative process of all the alphabets that we generate, and this is what the symbols of the alphabet, and you can see what they look like, and they can go on to infinity. And we see that you double at every point, and we can now use the word 2 because we've now generated the number 2 along with number 1. So we've created a logic and a grammar, and we still have the components of the conventional rewrite system, but we've no limit on any of them. And we've not assumed the symbol 1 in the first instance as a fundamental unit. It's a product of the system. Also, we don't have a halting problem that stops merely an arbitrary point in an infinite progression, which we will later show is irreversible and unique. There's no specific mathematical interpretation, but a very powerful one is an algebraic one. The anti-commutative objects have the properties of quaternions, square roots of -1, dimensional square roots of -1, and the I, J, and K, K simply comes as a look product of I and J. And we have infinite number of quaternion sequences. It's what we call a Clifford algebra. And this stage is the algebra of three-dimensional space, with vectors constructed from quaternions in that form. And we will need that later for the physics and other things. So the anti-commutative pairs now become successive quaternion units, each of which is commutative to all the others. By the fourth stage, we have repetition, and that continues indefinitely. An incomplete set of quaternion units becomes equivalent to algebra of complex numbers. So that's relativistic quantum mechanics. The most fundamental equation in physics uses exactly an algebra of this structure. And that is not a coincidence. Because it uses a commutative combination of the first complete Clifford algebra with all its subalgebras. It's creating it at the point of repetition. I will point out later that it's like the combination of a space and an anti-space, which creates a zero totality. And if you like, the sixth alphabet represents a particularly significant stage. And it's the first where the repetitive nature of the sequence becomes fundamentally established. This, we say, is the rewrite system order code of this process. And we can show that this process occurs in many aspects of the sciences. That had to be a bit technical because we can't justify ourselves unless we give you the technical background. So now you've had it, now we can talk about the consequences this afternoon. Okay? Thank you very much.